Hello everyone. Welcome to this class today, the thermodynamics class. So in the last class we talked about the work done by a reversible as well as steady flow device, and we also saw that how we can minimize the work for compressor. So today we are gonna talk about the topic 7.12, isentropic efficiencies of steady flow devices. So the topics itself is telling us that what are the conditions, right? So if we have a device that has steady flow, that means that pretty much constant amount of mass flow is incoming, and constant amount of mass flow is outgoing, right? So it will keep the steady flow, and then in this system also producing some work. So yes, in the last class we saw that how much is the work produced by this device. In other word, we saw that work producing, and we also saw that work consuming device. So if we have a work consuming device, which is a compressor or a pump, right? So this is incoming and this is outgoing, right? So then it's this device also consumes some work in this case. So this is compressor and this is turbine. So we know that work consumed by the turbine, if the process is reversible and steady flow, right? We know that expression. But today we are going to determine the efficiency. So what is the isentropic efficiencies for this type of like steady flow devices, right? So the first case is that isentropic efficiency of turbine. So isentropic efficiencies of turbine. So by definition, we know that efficiency is the ratio of the work output divided by work input, right? So in this case, isentropic efficiency of the turbine is the actual turbine work divided by isentropic turbine work. So let's see what is the isentropic turbine work. So if we draw a HS diagram, right, enthalpy versus entropy diagram, then we'll have the two different pressure of that system. For example, this is state 1 pressure and this is state 2 pressure. So let's express this one P1 and P2 for a turbine. Now the isentropic work done will be along this line. The entropy will remain same, right? However, in actual case, when we see that if pressure is changing, pressure doesn't change isentropically. So this is actually ideal case, right? Isentropic. However, the actual case is let me do it in different color. Actual case is like this. So then there is a difference between, so if this is entropy and this is enthalpy, there is a difference between this enthalpy, actual enthalpy versus the ideal enthalpy, right? Ideal enthalpy. So and also this one. So if we define these enthalpies, let me write it this way. Okay, so let's consider this enthalpy for state 1. This is H1 and this is actual, right? So this is actual and this is or let's say this is isentropic. So isentropic. So in isentropic case, we'll express this one as 2s and actual as 2a, right? So for we know that for this one the entropy is the same, but for this actual case entropy is different. So this for this case S1 equals to S2. So this is the TSHS diagram for the turbine. Now from this diagram we have to determine that what is the actual turbine work and what is the isentropic turbine work. So actual turbine work is nothing but this height, right? So from this point to this point. So if we consider or if we express that height by W actual, right, this height, and then isentropic work would be Ws, which is this height. So now if we try to plug in this isentropic turbine efficiency, then it will become isentropic efficiency of turbine actual work, which is Wa divided by isentropic work. So actual work, you can see from here Wa equals to H1 minus H2A, right? H1 minus H2A, whereas the isentropic work equals to H1 minus H2S. So this is the efficiency of this is the isentropic efficiency of a turbine if that turbine works as a constant mass flow rate or steady flow condition. So that's the efficiency expression we're gonna use in math problem. So now let's take a look for case 2. If what is the isentropic efficiency of a compressor? Isentropic of a compressor. So if it is a compressor, then the HS diagram will be, so this is S and this is S, right? So the HS diagram will be, for example, this is the, let me do it in color so then it will be easier for, okay. So this is the P1 state and this is the P2 state. So P1 actually for compressor pressure is increasing, right? So it will be high pressure and it will be low pressure. P1 will be this one and P2 will be the other one. So from this, for this case, from state 1 to state 2, it's going isentropically, right? So this is a isentropic line, whereas entropy is constant, right? But in actual case we see that it doesn't go in isentropically. So in actual case it goes, it bit deviated from the vertical line. So for this case, this is the actual process and this is the isentropic process, right? So again, if we put all those values, right, so this will be H2 actual and this will be H2 isentropic and this will be actual H1. So now we know that all those enthalpy values from this graph, right, we can calculate the isentropic efficiency of the compressor. So isentropic efficiency of the compressor eta C equals to compressor work, actual compressor work divided by isentropic. Actually for this case it will be, for compressor it's the inverse of or the reverse of the turbine. So it will be isentropic compressor work compressor work divided by actual compressor work. So in this case, the isentropic compressor work, if we take a look from this one, then the Ws equals to this height. Excuse me. Ws is this one, and actual is this one, right? So for Ws divided by Wa. So for Ws, from this diagram we can see it will be H2S minus H1 divided by H2A minus H1. So this is the efficiency for compressor if it is a steady flow as well as isentropic, right? So that's the efficiency condition. So now let's take a look another efficiency expression for nozzle. So if it is a nozzle, then what is the isentropic efficiency? Number 3, isentropic efficiency of a nozzle, right? So if the entropy remains constant for a nozzle, then the eta nozzle equals to actual kinetic energy of the nozzle at exit, and the isentropic kinetic energy at exit. So the kinetic energy expression, we know that V square divided by 2, but in actual it will be V2 actual divided by 2. Let me write it 2, and V2S divided by 2. So this 2 will be omitted, so it will become V2A square divided by V2S square. So that's the isentropic efficiency for a nozzle, and if it stayed at steady state condition, right? We can write one more expression for a pump, because we'll do some problem based on the pump as well. So the number 4 is that isentropic efficiency of a pump. So the pump efficiency, we know the definition of the efficiency of a pump equals to the isentropic work consumed or isentropic work of a pump, right? So isentropic work divided by actual work consumed by that pump. So the isentropic work for a pump, it will be in the last class we did a reversible steady flow device, and it was a pump, and we solved the problem, and we also derived the equation for the work consumed by that device. So that expression was V times P2 minus P1, right? And then actual work consumed by the pump and compressor, it's very similar, which is equals to H2A minus H1. So that's the relationship between the exit pressure and entrance pressure of a pump versus enthalpy of at the exit and enthalpy at the entrance. So if we know all those information, then we can calculate the isentropic efficiency of a pump. So this four relationship or this 4 efficiency equation we need for the math problem, right? If we mention that it's a steady flow device as well as the pressure change is happening isentropically, so that in those conditions we'll use this for efficiency formula. So now let's take a look at topic 7.13. Basically it says that entropy balance. So I mean, we already know that entropy of a system, right? If a system has multiple subsystems, then entropy generation is always positive quantity, right? um, but if a system is reversible, then entropy could be zero, right? And if the system is irreversible, then entropy generation is always positive. So that's the entropy increase principle. So for entropy balance for a system, if we consider a system that has, multiple system, right, that has a multiple system within this system, then entropy of this system equals to entropy, how much entropy is incoming, right, E in, how much entropy is outgoing, right, actually this is energy, right, energy outgoing, right, and then entropy will be S in and S out, right? And then total entropy generation, S gen, is always a positive quantity, right? So there is no way that it will be negative quantity. And then, so if this is the case, then for this system, entropy generation or entropy balance equation would be that entropy in, total entropy, or total entropy entering into the system, actually, excuse me, so into the system, that means S in, right, minus entropy out of the system, S out, plus entropy generation of that system equals to delta S of this system, total change of entropy of that system. So that's the entropy balance equation. So if we know that, if you see from this equation, we can see that the entropy change of a system, it's basically entropy equals to the summation of incoming entropy or plus generation minus the entropy out of that system. So if we know this relationship, we can plug in the incoming generation and outgoing, then we can determine the total change of the entropy of that system. So we know all those entropy changes. We derived this equation, how, what is the entropy generation, and if there is a heat transfer, what is the entropy change. So we talked about all those in the previous topic. So basically this 7.13 topic is the reminder of, or basically it's discussing the previous topics that we discussed separately. So this is a kind of combo that discuss of everything. So we'll go ahead and write some of the important formula that we discussed, right? So for example, if we have a steady flow process, right, so then for steady flow process, the entropy generation, for example, for steady flow process, the entropy generation rate will be equals to m s e minus summation of m I s I minus summation of delta k divided by tk. So this is basically the entropy transfer. Why it's entropy transfer? Basically it's exit versus input. So in exit, how much it's leaving the system and how much is coming into the system, that's the entropy transfer or the net entropy transfer of that system. And also we know that entropy transfer is also associated or related with the heat transfer. So so how much, if there is any heat transfer into that system or from that system, then how much entropy is transferred, that expression can be, or that can be expressed by this expression, right, Q over T. So this expression is entropy transfer by heat. Excuse me. entropy transfer by heat. So that's the expression so far for the entropy balance. So if you have incoming flow and outgoing flow, that is, that has the entropy, certain amount of entropy, and then also that system has the heat transfer, or some sort of heat transfer is happening, then the entropy generation will be this, and total change of the entropy of that system, we have to use this formula. So that way we can calculate that what is the entropy change of that system. So I think that's all about the theory, and I think we are done with this entropy chapter. So we'll go ahead and do some problem based on the isentropic and as well as the steady flow devices. For example, it could be pump, it could be nozzle, or it could be compressor or turbine, right? So we'll do math problem based on this topic. So I think that's all for this class, and thank you for watching this video, and we'll go ahead and math problem. Thank you.